situation here. We have a situation where we have a projectile launcher. We figured out that it launches an initial velocity of 6.38 meters per second. We're going to shoot it at an angle of 58 degrees. We want to know the range or the distance where it's going to hit so that we can set out a bucket and shoot this thing into the bucket. And so the first thing we need to do is break it down into its x and y components. And so for the x and y components respectively, for the x component, velocity initial in the x component, that is going to be equal to cosine theta, which in this case is the 58 degrees, times the initial velocity, which is the 6.38 meters per second. And so that'll give us the x component initial velocity. The initial velocity in the y component will be equal to sine theta, which again is the 58 degrees, times 6.38 meters per second, and that will give us that initial velocity in the y component. So let's see what those things are. We have in the x, I have cosine 58 degrees. I'm going to close my parentheses, times the 6.38. Make sure that you're always in degrees, not radians. And so that's going to give me an initial x component velocity of 3.38 meters per second. Then in the y component, I have my sine theta, which is the 58 degrees, times the 6.38 meters per second. That's going to give me a y component velocity of 5.41 meters per second. Now that you have x and y components, what we're going to do is firstly, I want you to understand, get rid of that. That should be like off of your mind at this point. You don't need that anymore now that you have x and y components. We are going to focus on the y component. We're going to focus on that. I'm going to write the initial equation just like it is in the book on page 68. I have the position final is equal to the position initial plus the initial velocity times time plus 1/2 at squared. And I think in the book they have this little bar over the a, which simply means that the acceleration is constant. That's what that bar over the a means. It means that it's average, or in this case, it really means that it's constant and not changing. Because when I throw something in the air, it is undergoing acceleration from gravity, and that shouldn't be changing as long as I can neglect air resistance. And so at low speeds, we can do that. All right, so the reason why we're going to use this equation is because we're going to look at the y component, and we have this acceleration. This acceleration over here is the acceleration of gravity. And remember that gravity acts in a negative direction. So I'm going to put in a negative 9.8 meters per second squared for that acceleration. If you see any equations that might look a little different, if I were to take some other equations might look like this. Just at the end, it's a little different. 1/2 gt squared, and it winds up being a negative. And so what you're doing in that case is you are making it so that way you were already putting the negative into the equation itself. So that means that you can use a positive value for 9.8. So if you see any equations that have a g in it, you don't have to put the negative in. Okay, hopefully you're clear on that. All right, so what I'm going to do is I'm going to take this away for the moment. I just want you to recognize that that's there. And we're going to work with this equation. Now, please understand that we're going to start at ground level, or what is virtually ground level, and we're going to finish at that same level. Finishing and starting at the same level, that's what matters here, and so it simplifies things quite a lot. So that means that the final position in the y direction, okay, this is going to be in the y direction. Put a little y there. This is the initial velocity in the y direction, and this is the acceleration in the y direction. You guys with me on that, I hope? And so the final position in the y direction is 0, and also the, excuse me, I'm sorry, not final, but the initial position in the y direction, that also is going to be 0. So since both of those two things are 0, I'm going to plug that in right off the bat. I don't like to plug numbers into my equations until later, unless it's 0. That's the only case in which I'm going to start plugging numbers in right away. If I recognize that something's 0, put it in right away so you can cancel stuff out. Otherwise, don't put numbers in. So I have 0 equals 0 plus the initial velocity in the y direction times t plus 1/2 at squared. So I've just changed my equation so that way I have the zeros in there and my really ugly t. And so now that those two things are 0, what this allows me to do is to factor out a t. So I'm going to do that. So 0 equals 0 plus, I'm going to factor out a t. Watch this. I have the initial velocity in the y direction plus 1/2 at. I've factored out one of the t's. And what that means is that there's two answers. The amount of time that it's going to be in the air, there's two answers. It's going to be in the air for 0 seconds. That means that it's at position 0 at 0 seconds. So basically, before I pull the trigger, isn't it at position 0? Yes, it is. Okay, so t is equal to 0. Okay, great, but that's not the answer I want. I want the other answer. Extending just a little bit more. So since t is equal to 0, meaning that t right there, my ugly arrow, that t is equal to 0, but that also means that all of this stuff here, that also must be equal to 0 for this statement to be true. So either this is 0 or all of this stuff is 0. One of the two must be true, and this here is what I'm looking for. Let me switch colors at this point, just for fun. So that means that 0 is equal to the initial velocity in the y direction plus 1/2 at squared. There's a plus. Thank you. That is a common mistake that I make. I make it all the time, so please don't you make it. All right, so we are going to just solve for t at this point. So I have negative diy equals 1/2 at squared. Gosh darn it. See, do it all the time. And that's, remember that if I wanted to, I can make that into a g that's negative. And so what that turns into, if I were to do that, I can just switch it around so that way this statement is true. I'm going to make that a positive now and make it into this. Okay, so finishing this off and solving for t, I have the initial velocity in the y direction times 2. I'm going to multiply each side by 2 to get rid of the 1/2. And divided by g. And that's going to equal my time. So this is the amount of time it takes for it to go up and come back down. And so since our initial velocity in the y direction, if we go back up, is the 5.41 meters per second, that is in the y direction. So my velocity in the y direction is equal to the 5.41 meters per second. So that's just going to go into my equation here. So 2 times the 5.41 divided by g, which is 9.8. Remember, I can put in a positive at this point since I made that switch. And that should give me a time of 1.104 seconds. 1.1 seconds is just fine. I just extended it out just to show you that it's there. But 1.1 seconds is just fine for my significant figures. 1.04 would be okay to use when you continue your calculations. Okay, now remember that I have the time it's going to be in the air. There's one commonality between the x and y components. The x and y components that we have way up here. This and this have something in common. They're both going to take the same amount of time to get to the end point. between the beginning and end, it's going to take the same amount of time. So time is the commonality. So I have 3.38 meters per second here. 3.38 meters per second. I can now use that at this point. Because remember that my velocity initial in the x direction is 3.38 meters per second. And since velocity, the initial velocity in the x direction, is going to be equal to the distance it goes divided by the time it takes to get there. So now I have, that means that the velocity initial in the x direction, hey, the velocity in the x direction, it doesn't change, remember? Only the velocity in the y direction will change afterwards. So that means that I can use this average velocity equation for the x component. So the velocity in the x direction, since it's not changing, times the amount of time it takes to get there is going to equal my x distance, which is my range. So I simply take my 3.38 meters per second in the x direction times the 1.104, just to be nice and legit about it. That gives me a distance, an x distance of 3.73 meters in the x direction. That is my x direction distance that it will go. So if I set this up, it's where I put the plunger all the way down into my launcher. It's going to eject out at 6.38 meters per second at an angle of 58 degrees, and it will go a distance of 3.73 meters. So if we put a bucket that distance away, it should, on the first shot, go in.